Alright, so to follow up our series on Rankine cycle, let's consider the question on the board. It says a steam power plant operating on a Rankine cycle receives steam from a boiler at a pressure of 4.2 megapascal and exhausts to the condenser at 3.5 kilopascal. Question says calculate the cycle efficiency. So first things first, we are given the pressures in both megapascal and kilopascal. And of course, we know that the steam table actually measures its pressure in terms of bar. So which means we have to convert these pressures to bar. So the boiler pressure was given, which is simply the first pressure or simply P1 was given simply as 4.2 megapascal. Okay, so we need to convert this to bar. We know that P1 equals 4.2. Mega simply means by 10 to the power of 5 Pascal. Okay, so sorry, mega simply means by 10 to the power of 6. All right, so we simply have 4.2 by 10 to the power of 6 Pascal. So we can actually break this down to be 4.2 by 10 to the power of 1. Okay, by 10 to the power of 5 Pascal, because actually 1 bar is actually 10 to the power of 5 Pascal. Okay, so we need to convert this to Pascal, or sorry, to bar. So this actually means that P1 is now equal to 4.2 by 10 bar. Of course, 10 to the power of 1 is still 10, so it becomes in bar because we have 10 to the power of 5 there. So this becomes in bar, and it's actually 42. 4.2 times 10 gives us 42 bar. So the boiler pressure is actually 42 bar. We also do the same thing for the condenser. Condenser pressure is P2, and P2 was simply given as 3.5 kilo Pascal, and we know that kilo simply means 3.5 kilo is simply by 10 to the power of 3 Pascal, and what we are looking for is actually by 10 to the power of 5. But then there's a way we can actually convert 3.5 to be 3.5 by 10 to the power of 3 to be 3.5 by 10 to the power of 5, simply by moving this decimal place 2 states backwards. So if you move it twice backwards, we're simply going to have that P2 is equal to 0.035 by 10 to the power of 2. If you multiply this, we are still going to have 3.5, okay, by 10 to the power of 3 Pascal, okay, which is this. So if we multiply 0.035 by 10 to the power of 2, we are simply going to obtain 3.5 by 10 to the power of 3 Pascal, which is still what we have there. All right, so if that's the case, now we can rewrite this equation as simply P2 equals 0.035. Now we have 10 to the power of 2 and 10 to the power of 3. So you simply pick up one of the 10 since they have the same base and add their powers. It becomes 2 plus 3, which is actually 5 Pascal. Okay, so this is actually equal to 0.035 bar, because 1 bar is equivalent to 10 to the power of 5. So if I have 0.035 to the power of 5, it simply means 0.035 bar. Okay, so that becomes the pressure of the condenser. All right, now having known this, now let's plot the diagram, or the TS diagram. So we simply have the TS diagram. It makes it easier. Temperature and entropy diagram. So it still remains, of course, this. Now, the boiler at a certain temperature and pressure, okay, heats up the fluid and sends it into the turbine at state 2. So this is state 1. We have pressure here, P1, given as 42 bar. Okay, and in this question now, we weren't given temperature. So normally we're supposed to have temperature, but we weren't given the temperature. So we simply work with the pressure that is given to us, simply 42 bar, down to state 2 in the turbine. So the turbine removes work from the system, sends it to the boiler, sends it to the condenser at state 3. Okay, the condenser removes heat from the system, turns it to completely liquid, sends it to the pump at state 4. The pump compresses the fluid back into the boiler and the process continues in that manner. So you simply have this. All right, so all we need to do now, since we weren't given temperature, it means we are going to work with the saturated water and steam table. So we'll go to the saturated water and steam table. From saturated water and steam, corresponding to the boiler pressure, which is pressure equal to, that's P1 equal to 42 bar. So we obtain what is H1 there, and H1 is actually equal to Hg. Remember from the previous video when I explained in the Rankine cycle, I simply said H1 equals the enthalpy at the gas for the first pressure or the pressure of the boiler. So H1 equals Hg. So you simply look up the saturated water and steam table corresponding to 42 bar. H1 equals Hg. What is Hg at 42 bar? 2577.2 kilojoules per kilograms. So that gives you Hg. Also, notice that state 1 and state 2 is isentropic, like I said. So it means they have the same entropy. So also you find S1, find entropy at state 1 under that same condition. S1 is also equal to Sg. So you find Sg at 42 bar. You have 8.219 kilojoules per kilograms Kelvin. So that gives you the value of the entropy at that state 2, at that state 1. Okay, so having known this now, next thing is to observe that state 2 is actually in between the gas and the liquid. So it's actually a wet vapor. Since it's a wet vapor, we need to find, remember the pressure at this point is P2, which is the condenser pressure. Now, the condenser pressure governs state 2, state 3, and state 4, while the boiler pressure governs state 1 and, of course, governs majorly state 1 only. So, we have to now find what is the enthalpy at state 2. Enthalpy at state 2, H2, is actually HF2 plus X2 HFG2. So we need to find HF2 at the given pressure at state 2, which is P2, which is the condenser pressure, and then HFG2 at still that same pressure. But then we don't know what the dryness fraction is. Since we don't know what X2 is, we need to find what is the degree of dryness at this point, because this is quite close to the gas region. So we need to find dryness fraction at state 2. So you recall we said earlier, we said that since S1, since state 1 and 2 is isentropic or is adiabatic, any of them goes, is isentropic, we simply said that S1 equals S2. So entropy at state 1 equals entropy at state 2. And that simply means but S2 itself, entropy at state 2 itself is still the same formula as this. But the only thing that changes now is what the thermodynamic property. No longer enthalpy, but entropy. Entropy is now, it becomes SF2 plus X2 SFG at state 2. So all we need to do now is to find SF2 and SFG2 at that given state. So corresponding to the given pressure at state 2, the pressure at state 2 was given as 0.035 bar. So we now go to saturated water and steam table. Alright, so we still consider from saturated water and steam table. From saturated water and steam, now corresponding to P2, which is the condenser pressure given as 0.035 bar. Okay, 0.035 bar. So all we need to do now is, first of all, let's find HF2. HF2 is simply equal to, under this pressure, 0.035 bar. So we move to the steam table now. Corresponding to pressure 0.035 bar, what is HF2? HF is simply 112 kilojoules per kilogram. So we'll find HFG, the middle one, HFG as state 2, 2438 kilojoules per kilograms. Also, we find SF2. So also under that same pressure, 0.035 bar. What is SF? SF is simply 0.391 kilojoules per kilograms Kelvin. And SFG, so SFG is simply 8.130 kilojoules per kilogram. So we simply have this. Okay, so having known SFG and SF, we simply plug it first of all into this equation for S2. Therefore, S2 is now equal to, we simply said SF2, and SF2 is simply giving us 0.391. So we have 0.391 plus, we have here X2, okay, Grani's fraction X2 times XFG2, and SFG2 was given as 8.130, 8.130. So we simply have this. So therefore, S2 is now equal to, this is 0.391 plus 8.130x2. So we'll keep this aside. Recall S1 equals S2, and we know the value of S1 already. S1 will obtain as 8.219. Therefore, but S1 equals S2. S1 itself is 8.219. So you pick it out. 8.219 equals S2, and S2 is the whole of this value, 0.391 plus 8.130x2. So we simply send 0.319 over here. It becomes 8.219 minus 0.391, and that's simply equal to 8.130x2. So we simply have this. So now you give me 8.219 minus 0.391. So you have 7.828 equals 8.130x2. So from here now, we can now be able to find the dynamic fraction at that state, simply x2. Let's do that over here. Alright, so we have 7.828 equals 8.310130x2. So we simply make S2 subject here. That gives us that the dynamic fraction at that point, x2, becomes 7.828 all over 8.130. This implies that x2 is equal to, give me the value. We have 0.96. So the dynamic fraction at that point at state 2 is simply 0.96. As can be seen, is very close to 1, and dynamic fraction can never exceed 1. It's usually between 0 and 1. So 0.96 simply means it's very close to the gas region, which explains that a little amount of heat was lost, which is why we have to find this dynamic fraction. And as such, to find enthalpy at state 2, therefore H2, I've said earlier, it is simply HF2 plus X2 HFG2. And of course, we've gotten the parameters of HF2 and HFG2 and the given pressure of the condenser, which is 0.035. Okay, so therefore H2 is now equal to, so under that pressure, we obtain HF2 to be 112, and we obtain HFG to be simply 2438. So we simply carry these parameters and plug into that equation. Okay. All right. So H2 becomes, HF2 is 112 plus X2 is known now as 0.96. 0.96 multiplied by HF2. Please call that value for me. 2438. So HFG2 is simply 2438. All right, so it means enthalpy at state 2 is now equal to 112 plus 0.96 times 2438. That gives us 2340.48. So therefore H2 is now equal to 112 plus 2340.48. That gives us 2452.48 kilojoules per kilogram. So this becomes the enthalpy at state 2. So we know H2 now, we know H1, we know H2. All we need to find now is H3 and if possible H4, but I don't think we need H4. The question says we should find the cycle efficiency. So first of all, we have to obtain the turbine work, and turbine work we already know is simply H1 minus H2. That gives us turbine work. So we know H1, we know H2, so we can simply find turbine work. Next is to find heat supplied, and heat supplied is simply H1 minus HF4. So the way to find HF4 is simple. HF4 is simply, of course, HF4 is simply the enthalpy at the given pressure. Since at the state 4, everything here is completely fluid, the pressure governing this state from state 2, state 3 down to state 4 is simply the condenser pressure, which is 0.035. So we simply go at 0.035 bar, obtain HF. That value of HF simply stands for HF4 at 0.035 bar. So at 0.035 bar, or from saturated water and steam, corresponding to 0.035 bar, which is P2 equals 0.035 bar, we can now find that HF4 equals HF at that particular state. So what is HF under 0.035 bar? So HF equals 112, and HF simply stands for HF4 because it's still the same condenser pressure that governs state 2, governs state 3, and governs state 4. So everything we're looking between these three states has to be under this condenser pressure P2, which is 0.035 bar. So we've gotten H4. The question is asking us to find the cycle efficiency. So to find the cycle efficiency, I've always said that pump work is usually neglected because the pump work is a very small value. So we usually neglect the pump work. So all we need to find now is what turbine work all over the heat supply. That gives us the efficiency. The efficiency of the Rankine cycle is now what turbine work WT all over the heat supply Q1 multiplied by 100%. So all we need to do is to find the turbine work, and in the previous video I gave means of how to find the turbine work even without cramming the formulas. And turbine work is simply H1 minus H2, and heat supply is simply H1 minus HF4 from that previous video. So you may please look up the previous video for proper understanding. Okay, so let's do that all over the other side. All right, so first of all, turbine work WT, we obtain that to be H1 minus H2, and we obtain H1 as what? So we obtain H1 as 2577.2 minus H2, and we obtain H2 over here simply 2452.48. So put that down, minus 2452.48. So give me 2577.2 minus 2452.48. This implies turbine work is equal to 2577.2 minus 2452.48. You have 124.72 kilojoules per kilogram. So this is the turbine work. Okay, so having known the turbine work, next thing is to find the heat supplied by the boiler, which is at state 1. So Q1, heat supplied by boiler. Okay, Q1 is actually H1 minus HF4, okay, and that heat supplied is equal to H1 also. We obtain the value to be 2577.2 minus HF4, and HF4 simply gives us 112 over here. So minus 112. What is heat supply? What? 2465.2 kilojoules per kilograms, and therefore efficiency, cycle efficiency is now turbine work, which gave us 124.72, 124.72 all over the heat supplied, which is 2465.2 multiplied by 100%. What's the value? So the efficiency is simply 5%. So it means this Rankine cycle is actually 5% efficient. So simply dividing these values and multiplying by 100 gives you 5%. So that's how to calculate the efficiency of that given Rankine cycle. All right, guys. So I will see you in the next video with more questions on Rankine cycles. So please take note, in this question, we weren't given temperature, so which means we have to work with the given pressures in the saturated conditions. But in subsequent questions, we'll encounter temperature, which actually means we'll have to look for the values of the um, first enthalpy at the corresponding temperatures and pressures using the superheated steam table. All right, please, if you find this video very interesting, don't hesitate to share your thoughts in the comment section, and of course, hit the subscribe button if you're new to the channel to keep getting content or updates on contents as this. I will see you in the next videos. Thanks and cheers.